Okay, so now, before proceeding with the next example, let's take a look at the input files that we use in the previous example. So let's go to the folder tests, folder 598 Final Project 2015, GFEMgl, and let's open the file used to define the initial global problem. We use the H version, and the file was with a mesh with 8 elements. So let's open this file with your favorite text editor. So here I have the input file, and start by providing one line where I have the number of nodes defined in this file, the dimension of the problem, which is 1, followed by lines in which I have the node ID, the number of dots at the node, and whether there is a special enrichment function at node, and finally the x-coordinate of the node. So for example, in this line, node ID equals 2, that node has 1 degree of freedom, and it has no special enrichment function, and the coordinate of the node is 0.125. So I have 9 lines with this data. After that, I have a line with a comment that indicates that the next line you have the number of elements in the problem, in this case 8 elements, and then as many lines with element ID, the first column, element type, property ID, and number of nodes. So for example, this is an element with ID 2 of type GFEM bar, the 1D ASCII bar that you are solving, property ID 1, and the list of nodes. These are the connectivities of the element. So this element 2 has nodes 2 and 3, and so on. So now let's define the properties. We use property 1 for all these elements. So this is the number of properties, only one in this example. The property ID, the type of the property, which is called Matlab periodic, the function number used to compute the Young modulus. This is function number 10 for this property. A and C are 1 for this problem. We don't have a distributed springs or anything else. So, sorry, A is the cross-section area, which is 1, and C is 0. C is non-zero only when you have a distributed spring in the problem. And BF number is the body force number. There is no body force in this problem, and so we have 0. So here, an important point is that we provide a function to compute the Young modulus, because the Young modulus is not constant for the problem, so we need to write the definition of that function in the Matlab source code. And we identify here the function number to use for this particular problem. So the function where the Young modulus is defined is called get_e. So look in your Matlab source code for that function, get_e. Next, we define the constraints, the Dirichlet boundary conditions. There are one constraint, which is the one applied at the left end of the bar, and that constraint is applied to node with ID 1. So that's the second entry in the line. The first one is actually the ID of the constraint itself. The second one is the ID of the node to which the constraint is applied. The third one is the DOF index in that node. So it's the first DOF in our example. And finally, the value of the prescribed displacement. In this case, the prescribed value is 0. And finally, the last set of data deals with the loads, the Neumann boundary conditions. We have one set of loads. The ID of the first load is ID 1. It's applied to node with ID 9, which is the ID of the node on the right-hand side, right end of the bar. And it's applied to DOF1 of that node and has a value of 1 unit. Okay, so that's the definition for the initial global problem that we use in the previous example. Next, let's look at the local problem. We use a local problem with mesh size 128. So L128, and this is used with a global problem with mesh size 8. So let's open this file. So the format is exactly the same as in the previous case. We have the definition of the nodes. In this case, we have 65 nodes. A 1D problem. So I have here the node ID, the number of DOFs, and whether I have enrichment functions for the node and their coordinate, x coordinate. So no node is enriched, so I have zeros in all cases for column number 3. Next I have the element data. I have 64 elements. Same format as in the previous case. They are elements of GFEM bar, the same as in the global problem. And this is their property ID and their connectivities. The properties are the same as in the initial global problem. Matti P bar periodic. The function used to compute the Young modulus, the same, since you are solving the same problem, the same physical problem, and so on. Now I have the constraints. These are the Dirichlet boundary conditions that will be applied. So one will be at node 1, and the second one will be at node 65. So those are the end nodes of the local finite element mesh. These constraints are applied to DOF number 1, and I have the value 0 here, because the value is actually provided by the initial global problem. So I just set the value here to 0, but I provide the ID of the global node from which we get the actual value to use in the simulation. So for the left node of the local problem, the constraint will be provided by the solution of the initial global problem at node 3. And at node 65 of the local problem, the boundary condition, the Dirichlet boundary condition, will be provided by the global solution computed at global node 7. And we have no loads applied to the local problem. Only Dirichlet boundary conditions provided by the initial global problem. And finally, let's look at the enriched global problem file, the file defining the enriched global problem. We are using the H version, 8 elements, and we are looking for the enriched global, so the EG in their name should appear. So that's the file. So let's open it. Similar format as before. Start by defining the nodes. There are 9 nodes, like in the initial global. So let's contrast the initial global with the enriched global. So everything looks the same, except that now for nodes, global nodes 4, 5 and 6, we have enrichment functions of type 10. And this defines that these nodes are enriched with a local solution. That's the enrichment type 10, the meaning of the enrichment type 10. Okay, so 3 nodes will be enriched with a local solution. All the other nodes are not enriched, as in the initial global. Everything else, I think, is pretty much the same. Yeah, the connectives are the same, material are the same, constraints the same, and load is the same. Okay, so the only difference is to indicate which node is enriched with a local solution. Only these 3 nodes. Okay, and also, since the node is enriched, it now has 2 DOFs instead of 1. Okay, so this is again the description of the input data files using the example that we just saw, and that's described in tab GFEMgl of the Excel file. Hi, so let's run now another example, and this time let's use the SGFEMgl. So in the SGFEMgl, as you remember, the enrichment functions are modified using the partition of unity of the global problem. So let's select the tab SGFEMgl in the Excel file. And here we have similar data as in the previous tab, the same convention for the mesh size in the global problem and the mesh size in the local problem. And we are going to solve discretization with global mesh size L over 8 and local mesh L over 128. So exactly the same meshes in the global and local problems as in the previous example, except that now we are going to use the SGFEMgl instead of the GFEMgl. Here I have the code that we are going to use and the input files for the 3 problems: initial global, local, and enriched global. So in our Matlab window, let's move to the folder. We want the folder Final Project 2015 GFEMgl SGFEM, so that's the folder that we want. Okay, so now let's run GFEMgl Junior. Let's enter the initial global problem input data file, hit enter. So you open the screen in the folder that we had selected earlier. We want a mesh with 8 elements, so H version 8 element. Local mesh 128 elements and 8 elements in the global problem. And enriched global 8 elements with EG in the name. Solving the local problem. Now solve the enriched global and compute the strain energy of the enriched global. And here I have the 3 figures showing the solution of the initial global, local, and the enriched global. Before you look at them, let's check if the strain energy that we got is the same as in the Excel file. So in the Excel file we have 0.25625, and here I have 2.562499, so except for small round-off error is exactly the same value. In fact, this is actually the same, it's just that Excel has truncated and rounded up the value for us. And if you look at the document with the problem definition, this is in fact the value of the exact strain energy. So in this case, in contrast with the previous example, when using the SGFEM now, we get the exact solution by using a local mesh that is fine enough to resolve the fine scale features of the solution. So this is the solution of the initial global problem. It's exactly the same as in the previous example. The solution of the local problem, again, exactly the same as the previous example. The only change is in the enriched global problem, that now we no longer see that those bumps in the blending elements, they are gone by using the SGFEM. And we get now again, in this case, the exact solution using the same number of degrees of freedom as before. So that's a nice result for the SGFEM. So the input files are very similar to those that I described earlier, so I'm not going to look into them. You can just check the folder with the files that we just used and compare with the previous ones used earlier. Okay. So so let's solve one more example, and this time we are going to use the data from tab GFEMgl linear enrich. So what does it mean? It means that we are going to use linear enrichment functions, linear polynomial functions, in addition to global local enrichment functions in the global problem. So we are going to use the same mesh size as before, L over 8 for the global problem and L over 128 in the local problem. And our goal is to get the same strain energy as the value shown here. So the files are in these folders, so we need to move to folder GFEMgl quad enrich. So let's go to the Matlab window, GFEMgl folder, quad enrich. Okay. So let me close these figures that we got with the SGFEM method. So again, GFEMgl Junior, input file for the initial global, we are in the quad enrich folder. Okay, that's where we want to be. Initial global problem, H version, 8 elements, as before. Local problem, 128, 8 elements in the global problem. And finally, enriched global, 8 elements, e.g. in the file name. So solve the local problem, now solve the enriched global, now compute the strain energy on each element. And here I have the solution for the enriched global, local, and initial global. Let's look at the computed strain energy. Again, we got the exact value. And so everything seems to be correct. The initial global solution is the same as before. The local problem solution is also the same. And the enriched global solution is the same as in the case of SGFEM, which means that there is no issue with blending elements when we use the linear enrichment in addition to global local enrichment. So the use of linear enrichment, linear polynomial enrichment, is an alternative to address the blending element issue. With that, we can conclude this example.